Okay, so doing an integral in x, y, and z. Let's say you have a surface. I'm going to call it f of x, y, z. Some sort of, oh, wait a minute. Oh, no, that's not, that's three-dimensional. Z is equal to a function of x, y. So that's a surface. For every point x, y, you plug it in and you get a z value. That's going to be z there. Okay, and then what you do is what you're going to be asked to do is take a region and integrate over that function over that region. So basically, you're finding the volume capped off by that, sitting over the region R and capped off by that surface. Now, you're going to set up a triple integral, obviously. And you can change the order. He tends not to do that. They tend to make you change the order when you have x and y and switch it and do y and x. He can make you do it here, but more often when it's three-dimensional, instead of making you switch the order of it, he makes you do it in a different coordinate system, cylindrical or spherical. But here's the rough idea on how to approach it. And we're going to approach it the same way for cylindrical. It'll be different for spherical, so we're getting to that. I'm doing this over this region. And so if I'm going to be doing z first, and let's say I am, obviously this is going to be z is equal to, and I'm not worried about the integrand, I'm worried about the boundaries, how you're setting up your limits of integration. So we're going to be doing z. That means y and z are to be held off for later, and so when I do this, it's the same thing that I do when I mention, like, when you got to do a two-dimensional region. I say if we're going to do dx first, then dy. So I say if we're going to do dx first, you pick a random y, because y is going to be treated like a constant first. So I just pick a random y there, and I slice along that y, and then we do that from there. Similar idea to that. I'm going to be doing z. Well, why did I write dy dz? Hold on. dy dx, my bad. We're doing z first for sure. That's usually what he wants you to do, or he usually sets it up so that you're doing z first. I think Crew gave you ones where you might have to reorient it, but let's not worry about that. Okay, I'm doing with respect to z first. That means y and x are going to be treated as constants, which means just like when I pick a random y or a random x, depending which I'm slicing, here I'm going to pick a random x comma y. So amongst here, some random x comma y, bam, right there. It's my random xy pair. And then along there, I'm going to do a slice along that xy. That's just a random xy, and I'm going to do a slice. And that slice is not really a slice, it's like a spear, piercing. Bam, it hits there. Goes down, and then comes out the other end. So it's getting capped off by the surface and the xy plane. Let me clean this up. So if you're going to do z first, you're always thinking about a little straw being inserted into your boba drink and hitting the lid of it, and then going down to the bottom of the cup. Okay. And now my z's are upper minus lower. What's my upper one? My upper one is the actual function, the surface. And I'll have an expression. It won't be a constant. It'll be an actual function in xy. What's the bottom? The bottom of the cup is the xy plane. The xy plane is the equivalent to z is equal to 0. Okay. And then I have to do dy dx or dx dy. So he will let you switch these. Not let you, I mean you can switch anything you want, but he will have it where you have to kind of think this through and think about which way is better for you. But once you get to this stage, what you're doing is you're just integrating over this region in xy. So at that stage, you switch to a bird's eye view of the xy plane. And then you're trying to do this region, which I'm going to try and draw it the same way. It looks like that. This is not a nice one. I'm not going to be able to actually do it. But then you figure out these boundaries. either x first and y second, or y first and x second, but doing what you did in 2 dimensions. You've already covered your z. So I'm going to be thinking of it like this. I'm going to focus on my z, and then for the last two, my dx dy, I'll just do whatever I did when I had to switch the order, do different things. That's the idea. I'm going to be treating the first layer of integration as just slicing a straw into your boba, and then these two I'm going to be creative about how I'm going to get that region when it's a weird one. Okay, so moving on to not your actual inertial problem, but the problem you're working on. Well, for now it's right now as you're complaining about not knowing how to do it, but I don't know how long it's going to take this video to upload, so it could be the entire next day. Let's see. And I just made up some random thing. What did I say? X plus y plus z is equal to a, what did I say, 2? I don't know. I'm gonna, if it's not the same problem, I'm making up a new problem. Bounded by, that's a plane, which I probably want to think of it as z is equal to 2 minus x minus y. So note that. Because I like that before I wanted z is equal to. Okay, let's see. Let's pretend I don't know that. Hold off. Okay. Bounded by the xy plane. And the cylinder, I think I wrote x squared plus y squared is equal to 4. Okay, I gotta know what all these things look like. At this point, he will expect that of you. Okay, x squared plus y squared equals 4 is a circle of radius 2, because that's radius squared right there, 4. So radius 2, and you get a circle of radius 2. Oh shit, it's off. Except it's not a circle. This is 3 dimensions, and this is specifying that x and y have to always have this relationship. But z could be anything. There's a z coordinate for all the points, so it's basically, it has to be on that, but z could be anything. So it ends up being this cylinder that extends negative infinity down to the, negative infinity of z, infinity up to positive infinity on z. Except that I'm capping it off with the xy plane. So I'll get all that. So we're capping it off on the bottom. That's the bottom of your cup. And on the top with a plane, which is not flat, it's going to be an angled plane. I don't know how it's going to be angled. I don't care how it's going to be angled. But it's basically going to take your thing and you slice it at an angle. You take a little knife and you cut it. It ends up cutting it so it looks like a little pencil holder. I don't know what you want to look at it. But anyway, it slices at an angle. I don't need to know the angle or anything like that, but I know it's just not going to be a flat one. So let me draw that in. So I'm going to cut it at this weird angle, even though that may not be an accurate depiction. I don't need it to be super accurate, because I just want to visualize my region. And now I'm going to set up my integral, and I'm ready to go. Now, because my bird's eye view of it will be a circle of radius 2. Some professor calls this a shadow. Some people call it a footprint. So the idea is, whatever you're doing up here, slicing it that way, the footprint of the region is what we have to do in the xy plane. But we're going to hold off on that. I'm going to do my z's first. And so now I'm going to do what I did before. I'm going to pick some random xy in my region. Right there, bam. Which is equivalent to here. Bam. And right there is where I'm going to insert my straw into my boba drink. It's going to go into my angled lid. Dot, 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 dot. Bam, it pierces it right there. My straw is going all the way to there now. And then, well, I mean, doesn't follow the metaphor, but it'll then come out the other side, that slice. Okay. And where is it? Uppercut. The uppercut is that plane. Where's the lower cut? The XY plane. So that's based on the upper plane, lower plane. That's where my bowl straw is going through. Okay, my upper plane is this, but I don't have it. I need it in the form z is equal to, that's why I should have solved it. 2 minus x minus y. That's my upper bound. What's my bottom? The xy plane. You have to interpret that as a z is equal to. It's z is equal to 0 plane. All right, and then I'll have whatever integrand I'm trying to do. If it's just the volume, I'm just doing 1. Then you don't need the parentheses, but I'm going to put them side by side. That's a separate thing. And now I'm going to do a double integral dA for like an integrating over an area to do this. And I can do it in rectangular, but then it's going to have like square roots of 4 minus x squared or something like that. I've got to do circles and solve circles for an upper half and a lower half, a positive and negative square root. Those forms of half circles, because it's going to be upper half, lower half if I do it that way. Not good. Not the best way to do it, because he wants you to take advantage of the fact that it's circular around the origin. So what's best to do there is, and this dA means you have a choice. You just got to do an area, and you can do it whichever way you want. And our two common options are rectangular with dx dy, rectangular with switching the order of integration if that's convenient for you, by all means. Or if it has a circular nature to it, polar, dr d theta, which means combining with this, that means we're doing cylindrical. Polar there with the z coordinate makes it a cylindrical, which means if I'm going to do that, I hadn't decided it earlier, but now that I realize I'm going to do that, I need my Jacobian. Okay. All right, and now I'm going to do this. These two outer integration, limits of integration, purely based on no longer looking at a picture, but just looking at the shadow, the footprint on the xy plane. And how am I going to do that? It's going to be r first, generally. And I can think about taking, I'm not doing that anymore. I'm thinking about taking a random, I'm going to treat theta as a constant, so I'm going to take a random theta slice. I'm going to find out what my outer curve is. My outer curve is r is equal to 2. What my inner curve is r is equal to 0. So r is going from 0 to a constant 2. May not be a constant, it could be a function of theta still, but no, this one's perfect circle, it's a perfect constant. Last thing, oops, not r, theta. Theta goes from what to what? Now this one is the entire thing, but later on he will be making you do things where you're only going to take like half of it. He might make you take like, let me think, this half. Let's say that half. Which means I would have had another bounding curve. I would have had that bounded by that, and another plane slicing it there, which I could have done. I don't have time to go through that many examples. But if that were the case, you go negative pi over 2 to pi over 2. If it's a full circle, which it is, we're just going to 0 to pi. But, sorry, 0 to 2 pi, what I'm talking about. And that'd be the setup for this. So you're going all the way around from 0 to pi, but again, he would give you different sections of that, slicing it off this way, so you only get parts of that shadow, or that footprint. Okay, so we're not doing rectangular. This is cylindrical. You're going to be doing cylindrical for that thing, obviously, because it's got this cylindrical, circular nature. We'll talk about that when we get there. Anyway, that's all I got.